presentation, I have the great pleasure to introduce to you to Professor Amitava Sen Gupta. He is our last international speaker. He is for the NorthCap University, Gurugram, India, and he is going to talk to us about Cesium fountain frequency standards at NPL India. We give him a great thank you for being here.
Thank you very much. Good afternoon. Let me, right in the beginning, say that I'm really very thankful to Dr. Mauricio Lopez and his team, Karina and Neen, for giving me this opportunity, for inviting me to come here and talk about cesium fountains. And as Karina said in the last session, one of the biggest findings of this workshop is that time is very important. It's also one of the units that has been measured most precisely, as Professor Bill Phillips talked about in his talk yesterday. And also we had a wonderful presentation by Eckhart Pai, and we had another presentation on time and cesium fountains in the last session from Sinam. So, well, basically, I thank my colleagues at NPL. I'm no longer at NPL, I've retired a few years ago, but I'm going to discuss the work which was done at NPL India. Now, let me just say that my talk is very, very basic, so some of you who are experts on the subjects, kindly bear with me. This is more like an undergraduate description of what is behind the fundamental principles behind atomic clocks, the basics, and the basic principles of how a cesium clock works and how we improve it to go to a laser-cooled cesium fountain, and then we'll discuss some results. But all this is very simple descriptions. I'm not going to do the state-of-the-art description like Eckhart did in his presentation. So let's just say that the ingredients of basic clock, as I told in the panel discussion, basically it's in a clock, you have a source of frequency, a periodic phenomenon. This periodic phenomenon could be a pendulum, or it could be the rotating earth, or it could be a quartz oscillating at a uniform frequency. So something that changes periodically. And then you have a counter to count the number of cycles of the oscillation and something to display the time that has elapsed. But you quickly realize that the counter and the display units don't really make much of a difference. They don't make mistakes. So these are mundane. So basically, whenever we talk about clocks, we talk about the frequency source associated with clocks. So we are, in particular today, going to talk about atomic clocks, where we use atoms as tiny oscillators. This is high school description of what is in atoms. You have a nucleus, you have electrons, and if you can have a single isolated atom which is not perturbed by anything else, the electron goes in discrete orbits, and when it jumps from one orbit to another, it is associated with a photon, which is given by this relationship. And somehow, if you could use this frequency as that frequency with which you make your clock, then you'd have a perfect such clock, because an atom of cesium is an atom of cesium no matter where in the universe you take it from. So you would have the most perfect clock in the universe if you can use the frequency out of a clock. And when did it begin? It didn't begin very long ago. Just about 75 years ago, January 21, 1945, Professor Isidore Rabi, in his American Physical Society meeting, was the one that proposed that the oscillations inside atoms be used as a clock. So that was the first time when atomic clock was proposed. And Rabi's student Ramsey further improve this concept, separated oscillatory field. We are going to discuss this in a little bit. So that's how the activities in atomic clocks began. So inside an atomic clock, basically what we do is, it's a device that makes use of stable atomic transition frequency as its reference, a quartz oscillator. Because the atomic frequencies, these transition frequencies are weird numbers, and also the signal that comes out of the atoms is very, very weak. So usually we use a quartz oscillator and lock it to the atomic transition to give a usable output of an atomic clock. So the schematic looks something like this. You have a quartz oscillator and you synthesize a frequency which equals the atom's transition frequency. You interrogate the atoms and it shows a sign that it has responded, the frequency is right. That means you locate the peak and then servo that signal to lock this oscillator to a particular peak or a resonance of an atom. So that's basically the schematic of an atomic clock. Now, some of the important considerations for making an atomic clock is you have to select a suitable atom, you have to select a suitable atomic transition, and then you have to prepare the atoms, because we said the atoms have to be in, they cannot be in liquid or solid state close to each other, because as Eckhart said in his talk, if you have atoms close enough, the electronic transitions are no longer discrete levels, they're bands. So then you have to get the atom to come together and stand in front of you, that you have to confine the atoms, and then you have to interrogate the atoms with the signal that corresponds to its resonance. So selecting suitable atoms, now we are talking about 1950s, lasers had not yet been invented, so it turned out that the most suitable atoms were the atoms in the group 1 elements. And it turns out, I'm not going to go into details, it turned out that because these are attractive because they have one unpaired electron in the outermost orbit, that's the valency electron, and they are easily ionized. So in 1950s, that was the only way in which you could detect atoms in an atomic beam, ionize them, and measure the current. So cesium, rubidium, and hydrogen have been traditionally the favored atoms for making atomic clocks. Now, of course, we have plenty of other atoms in trapped ion and other such systems. And then selecting suitable transitions. Now, the cesium atom has a ground state and a host of excited states. And now all these transitions traditionally are in visible and infrared and so on. But again, we realize that we cannot be using these transitions for making atomic clocks. We are talking about 1950s and 60s, when lasers had not yet come in. So we had to do something else. So usually the atomic frequency standards are based on magnetic hyperfine transitions in the ground state. And just again a high school description, you have in an atom a nucleus with a spin, an electron with a spin, and these two spins, the nucleus spin in cesium is 3.5, electron spin is half, and these two can be parallel or anti-parallel. So in case they're parallel, you get the quantum number F equal to 4, and when they're anti-parallel, F equal to 3, and these two states have a slightly different energy. So that's the hyperfine transition that we are talking about. So basically, the ground state splits into two states which are very close to each other, and the difference corresponds to microwaves. And in 1950s, thanks to the Second World War, there was a lot of development in microwaves. So microwave technology, so this was very easy to handle with the available technology at that time. So this was what was used as a clock transition in the first cesium clocks, and it has continued till today. Now the problem is that in a distribution of energy levels in this way, the population distribution is governed by Boltzmann law, and most of the atoms at normal room temperature are in the ground state. The probability is 1, and all these excited states are literally unpopulated. But unfortunately, our F equal to 4 and F equal to 3 are both at the ground state, and there is no difference in their population. There are 50% of the atoms in the ground state are in F equal to 4, and 50% are in F equal to 3. And unless we have atoms only in F equal to 4 or F equal to 3, we cannot interrogate, because if we do, then the 3 atoms will go to 4 and 4 will go to 3, and next result will be 0. So in some fashion, we have to do state selection. And this is how we do. We can consider cesium atoms in the ground state as tiny magnets with only 2 possible orientations, F equal to 4, let's say, are very simple, just a visual description. You can consider these as atoms with magnets pointing up and magnets pointing down. Now, if you pass these through a strong magnetic field gradient, transverse direction, and if I have an atom passing through this, it deflects in one direction, and if the orientation is the other way, it deflects in the other direction. So depending on whether it's in this state or this state, they separate out when they go through a magnetic field gradient. So that provides us a convenient way of doing state selection, separate or sort atoms depending on which state they are. So let's understand the working principle, fundamental working principle of an atomic clock. You have an atomic source, an oven. Now cesium at room temperature is almost liquid, so you just have to heat it just a tiny little bit, and a thin stream of cesium atoms comes out, and they're all in ground state, and 50% of them are atoms pointing up and 50% are F equal to 3. So when you pass them through a state selector magnet with a strong field gradient, half of them go this way, the remaining half go the other way. So you have achieved state selections. You block this and allow only one kind of atoms to go through, and then they pass through a microwave cavity, through a hole here and a hole there. So it passes through the microwave cavity and goes through another similar magnet, which is called the analyzer magnet. And then you shine a microwave frequency, microwave signal on this. And as long as the frequency does not correspond to the transition frequency, nothing happens to these atoms. And as you scan across the resonance, when you hit the right frequency, the atoms flip to the other state, and instead of going this way now, they go and fall on the detector. So now you detect a signal, aha, so now I know that my microwave frequency is right, and you use this signal in the detector to lock the microwave source so that it would stay on top of the resonance. So that's fundamentally what is inside an atomic clock. Rest is a matter of detail. For instance, you have to have the whole thing under high vacuum. You have to shield this from external magnetic fields and lots of other things. And another thing that we have to see is this. You have a stream of atoms going through the microwave cavity, and these atoms are thermal atoms. They're moving with a few hundred meters per second through this length. If L is the length of this interaction region and alpha is the most probable velocity, then the time the atoms spend through the microwaves is tau equals L by A. That's the time the atoms see the microwaves. That's the interrogation time. Now, it turns out that when you have the atoms seeing the microwave for time tau, then the probability that they will make a transition looks like a Gaussian, and the maximum probability happens when this condition is satisfied. This is the transverse Ravi oscillation frequency, which in a way is directly proportional to the microwave signal intensity. There's some relation. So omega t times tau, the product is equal to pi, gives the highest probability of transition. And in an atomic clock, we want to maximize this probability, and you want to lock the the microwave frequency, external microwave frequency, to the top of this resonance. So the higher the peak and narrower the peak, the more precise your clock is. Now, we have already made it highest by making this product equal to pi. So this is traditionally called subjecting the atoms to a pi pulse. The atoms see a pulse of microwaves equal to the product of this is equal to pi. So this is called a pi pulse. And the line width of this transition frequency is given by delta is pi divided by the time of transit. So the line width is inversely proportional to how long the atoms spend in the microwaves. Now, it's clear that if you want a better clock, if you want a more precise clock, you have to increase the length because then the tau reduces, tau increases, and when tau increases, you get a narrower line, and hence you get the top of the peak is sharper, you get a more precise clock. But the problem is that if you make a longer interaction region, longer microwave cavity, then there are inhomogeneities in the microwave signal inside the cavity. And that means that this curve is no longer valid. So a way around this problem was solved when Professor Norman Ramsey came into the scene, and he said, there is a cleverer way of solving this problem. He said, instead of one cavity, let's have two microwave cavities of each one. Instead of a pi pulse, you give a pi by 2 pulse. So the addition of these two will be a net pi pulse, but these two are separated by some distance, capital L. Now, instead of one cavity, we use two identical ones separated by a distance along the cesium beam, each driven by an oscillating field having the same phase was the condition. The space between the cavities does not have to have microwaves. It has to have, however, a DC magnetic field through which the atoms will precess, right? And when you have that, then it turns out that the probability curve is narrower. The line width becomes 1 over T, capital T. Capital T is L divided by alpha, capital L divided by alpha, which is much longer. That's separation between the two cavities. So this can be made narrower. So the sharpness of the resonance is not reduced by non-uniformity of the constant field, because now each one of the cavities is very narrow, so we don't have to have non-uniformities inside these. And provided there is no unintended phase shifts between two oscillatory fields, the first order Doppler shifts are eliminated. So this was a major improvement in the atomic clock technology, which is followed still today, the separated oscillatory field technique. So let's just quickly go through the schematic of a modern day cesium atomic beam clock. You have an atomic source, you heat it a little bit, have a tiny amount of cesium here, and you get a cesium beam, and then there's a strong magnetic field gradient, and you block one of the kinds of atoms, you allow the other kinds of atoms to go through microwave cavity. There are two parts of the cavity that it goes through, the separated oscillatory field, and then it goes and either hits the detector or it doesn't, depending on whether the microwave frequency is right or not. The separation between these two is the time that decides the width of the so-called Ramsey fringes. So this fringe is called the Rabi fringe or the Rabi pedestal, and the width of this is inversely proportional to the time the atoms spin inside this, which is a very short time, and hence this pedestal is very wide. But the actual Ramsey fringe is very narrow. That is proportional to 1 over T, which is the separation between these two ends of the cavity. So today, a commercial cesium atomic clock looks like this, and you can get an accuracy of 1 part in 10 to the 12. And inside a cesium beam clock, see, this is the two ends of the microwave cavity. The atoms go through this end and that end, and this separation is the separation that decides the interrogation, Ramsey interrogation time. And typically this is about 20 to 30 centimeters across, and the atoms having the normal thermal speed, it turns out the interrogation time here, the Ramsey interrogation time is 4 or 5 milliseconds. And when that happens, you get an accuracy, you get a width of something like 100 to 200 hertz of this Ramsey width, and that gives you an accuracy of 1 part in 10 to the 12. Now, if you wanted better clocks, you have to have longer beam tubes. So in the 90s, they indeed built longer microwave cavities. You know, these are efforts at NIST. This is NBS4, NIST 7. I mean, I believe this had a microwave cavity which was more than 1 meter across. But then you quickly realize that you cannot build it longer and longer because your gain is only linear. So in order to get a cavity, in order to get a clock which is 10 times better than this, you have to have a clock that spans the whole building. There's no end to it. So an alternative concept which had been proposed in the early 50s was, instead of shooting the atoms horizontally and making them go through two ends of a microwave cavity, let's shoot them vertically. And if we launch the atoms vertically, then due to Earth's gravity, they would go up, go through a cavity, and then come down through the same cavity. So this could be the two separated oscillatory techniques. So that's the initial concept of the cesium fountain. So now your Ramsey interrogation time would be this time, which could be about half a second or so if you shot it about 1 meter high. Now, and this way we can get much longer interrogation times, and the big advantage is that both separated fields are produced in the same cavity, so there is no phase shift between them. It's identical. The same cavity goes through one way and the other way. However, we can't use thermal atomic beams at room temperatures because atoms shot vertically upwards at a few hundred meters per second will not come back. They'll go hit the ceiling. You know, so this concept could not come into existence till laser cooling was invented. So thanks to, I'm not going to talk about how laser cooling is done. I think we've had a lot of description of that. Now, basically, there are two ways in which we do laser cooling in cesium. We use the cooling transition at 852 nanometers. There are two lasers that we use, and we use 6 orthogonal beams of lasers. We use a cooling laser that pumps atoms from the ground state F equal to 4 to 5 dash, and this is a cyclic transition, so the atoms oscillate between these two levels, and the atoms which are, and once in a while they fall down here, which are repumped to the F equal to 4 level by the repump laser. So by doing this, you get a cloud of atoms which is typically about 8 to 10 millimeters diameter, and the number of atoms in the cloud is about 1 million to 10 millions. You can also have a more intense cloud, shorter diameter, by using a mott instead of a molasses. But however, no matter whether we use a mott or a molasses, we don't get atoms which are cold enough. We still have to do further cooling to get down to lower temperatures. We are going to talk about that in a little bit. So then we use the present day concept of laser cooled cesium fountain. We use 6 orthogonal laser beams, produce a cloud, shoot it up vertically to about 1 meter high approximately, and we interpose the microwave cavity in between. The atoms go up through the cavity, up and back down again. So this is the Ramsey interrogation time. Now we can no longer in this system use a magnetic state selection because then the atoms will deflect. So the state selection I'm going to just discuss is done by using optical pumping, and we detect the atoms not by making ions and detecting the ion current. We make use of the detection by fluorescence. So state selection by optical pumping. Normally, as we said, in the ground state, the atoms of 4 and 3 states are equally populated. But when you shine the lasers on them for laser cooling, these F equal to 4 atoms cycle between, thanks to this cooling laser, they cycle back and forth between 4 to 5 dash. But however, the atoms in state 3, they are pumped to this state. So finally, very soon, all the atoms end up in the state F equal to 4. So by virtue of this process of laser cooling, we also achieve state selection. But however, this is not yet complete because we know the atoms have to go through a DC magnetic field, and when that happens, these states, each one of these states is further subdivided into Zeeman sublevels, and there's a whole host of them. There are 9 here and there are 7 states here, and the atoms in F equal to 4 are distributed among these 9 sublevels. And we are interested in our clock transition, which is only 4 F equal to 4, MF equal to 0 to F equal to 3, MF equal to 0 state. That is our clock transition. So now, if I may elaborate on that, so my F equal to 4 atoms are actually evenly spread among all these Zeeman sublevels, but I'm just interested in these states, 4, 0. And for that, we do a little extra trick. What we do is, instead of the regular cavity, we in addition have a state selection cavity just below the Ramsey cavity. That is called the state selection cavity, and the atoms, when the atoms are just passing through the state selection cavity, we shine a pi pulse of radiation corresponding to the clock transition. And when I shine the pi pulse, only these atoms in 4-0, they make a transition to 3-0. And immediately afterwards, we shine a laser beam from top. We switch off all the rest of the laser, we shine a laser beam from the top, and that kind of blows away all the remaining atoms in the other MF states. So finally, when the atoms go through the Ramsey cavity, you are left with only these atoms, F equal to 3, MF equal to 0, and they are subjected now to the Ramsey interrogation of 1 pi by 2 pulse on the way up and a pi by 2 pulse on the way down. So that's how we do state selection. And again, now the entire physics package of the cesium fountain looks like this. The gray shaded area is all ultra-high vacuum. Typically the vacuum level that are needed inside such a cesium fountain is about 10 to the minus 9 or a few parts in 10 to the minus 10 torr or so is required for a decent operation, so that you'd have a nice beam which is not obstructed by the background gas. So we cool the atoms in this area. This is the Mott chamber, and we shine 4 lasers in the horizontal direction and 1 laser from top, 1 from the bottom. So that's the cooling in this area. Then we launch it through this, through the state selection cavity, through the Ramsey cavity, up and back down again, and this is where we do the detection. And of course, rest, as I said, there's a lot of details. You have to have a uniform magnetic field, which is the DC field, and then you have to have several layers of magnetic shielding around it to get rid of the stray magnetic fields due to Earth and other things. So the optical setup of the cesium fountain basically comprises a master laser for cooling which is locked to by saturated absorption spectroscopy, which is locked to the 4 to 5 dash transition of cesium. And then of course we have a whole set of AOMs to be able to very precisely shift the frequencies, to Doppler shift them for laser cooling, further Doppler shift them in a certain way for polarization gradient cooling, and the 2 vertical beams to give the atoms a push for launching. So all those are a lot of details, and the final optical setup is quite complex. And finally, we have 6 laser beams for the cooling and launching, and we have 2 laser beams for detection. I'm not going into all those details because that will take a long time. So, and this is typically how the optics looks like on the table. And one of the things that makes this somewhat different from a regular optics experiment is here is an experiment which is not intended to be done for just a few hours, and when you are done with the experiment you disassemble and be done with it, because this is something which you want to continuously operate over days, months, and so on. And the laser locking has to be robust enough that will not get unlocked every once in a while and so on. So you take a lot of precautions to do that. So finally, this is how the cesium fountain in NPL looks. This is the physics package. The atoms are cooled down somewhere here. They're launched through this about 1 meter high and so on. And this is where the optics is and all the rest of the electronics. The fountain operates in a sequential manner. The first point in the sequence is cooling and trapping. We showed with 6 orthogonal beams, and then we launch it by having only the 2 vertical beams and frequency shifting them by a moving molasses technique. And as soon as the atoms are launched, we further cool them by polarization gradient cooling or sub-Doppler cooling. And then we also do state selection in the way that I just described a little while ago. And then the atoms go through the microwave cavity twice on the way up and then on the way down. And after that, they would have made a transition, which is detected by fluorescence. So that's the operational sequence. And a little bit about the electronics and control of the cesium fountain. Basically, we have to generate a microwave frequency corresponding to the resonance of that clock transition, and we scan it across the resonance. And this frequency is usually referenced to a 5 megahertz very low noise oscillator, which is again referenced to the hydrogen maser, which is a part of our time scale. And then this low noise oscillator output goes to a synthesizer. I'm not going to go into the details of the synthesizer, and except saying that an important part of the synthesizer is a DDS, a direct digital synthesizer, which has a resolution of better than a microhertz. A microhertz in 10 to the 10 hertz, that's about 9 gigahertz, is an enormous resolution of about part in 10 to the 17 or so. That's how finely you'd like to be able to shift the microwave frequency as you scan across the resonance. So we shift the scan across the resonance of this transition, and we apply this microwave frequency to the fountain package and do data acquisition and see how the atoms are doing with respect to making the transitions and so on. I mean, while we are at it, I thought we'd just show you how the atom cloud looks. We just put a CCD camera by the side of the fountain, and so initially the cloud is tiny, that's a mod, and then you allow it to cool further in the molasses, the cloud becomes bigger. Then of course you can't see the cloud being launched because you have to switch off all the lasers, then it becomes dark. So that's how our atom cloud looks. And then on the way down, when the atoms go through the detection region, there are lasers that shine on the atoms on the side, and the atoms fluoresce, and depending on what frequency of the laser that you're shining on the atoms, you get fluorescence first from the F equal to 4 atoms, and then these atoms are blown away, and then you get the red curve, which is the fluorescence from the remaining atoms in F equal to 3, which have not yet made a transition. So the transition probability is the total number of atoms, that is, number of atoms that have made the transition divided by the total number of atoms. This is the transition probability that we measure with this. And the number of atoms is deduced from the area under this curve. So, and we have a data acquisition system which is completely automated in LabVIEW. Here you can't see this very clearly. You see these the signals of detection, and this is the transition probability, and it's logged continuously. This is, I think, a few days data. So this kind of a GUI appears on the computer. So finally, the end result, 5 minutes? Okay, I'll be done. So you get the Ramsey fringes. See here, I've just expanded this. The clock transition is this Ramsey fringe in the center, whose width is a little more than a hertz, 1.5 hertz, and this is the Rabi pedestal. Now, I just briefly say something about this. I mean, ideally, the width of this is inversely proportional to the time the atoms spend in the Ramsey cavities, and the width of this is the total time, capital T. So this is inversely proportional to this Ramsey width, and so on. Now, one of the things that I did not show the atoms have a finite temperature, so as you launch them up, they expand because the atoms are not very cold. So when they expand, on the way down, if the atoms are not cold enough, not all of them manage to get back through the cavity. So there are two things that happen because of that. Firstly, your signal to noise reduces because you don't get back as many atoms that went up, you don't get back so many of them. And secondly, there's a velocity dispersion in a cloud in which the atoms are moving relative to each other. So because of the velocity dispersion, these Ramsey fringes wash out before they go to the end. So ours is not the best fountain in the world, but some of the best works, I mean, I've taken it up from another paper from, I think this is the French group, and you see the Ramsey fringe of less than a hertz width, and the fringes go all the way out. So this is what would be in case of really cold atom cloud, better than close to a microkelvin. In our fountain, it's about 5 or 6 microkelvins or so. So, and finally, if you build a clock out of such a device, you get an instability of that clock, which is like this, 6.5 10 minus 13 at tau, the minus half square root of tau, and it hits 1 part in 10 to the 15 close to a day. Again, as I said, this is not the best fountain in the world, but some of the best fountains at PTP, for instance, they hit 10 to minus 15 at about 10 to the 4 seconds or so, and their accuracy is few parts in 10 to the 60. I'll quickly go through the estimation of uncertainties. See, the total uncertainty in the clock that we have just built, that is a Cesium fountain, comprises 3 parts. One is the statistical uncertainty because of a finite signal to noise and so on. This is the random jitter. Then there are systematic uncertainties. Then there is an uncertainty in the comparison between your fountain and the rest of the world. If you want to contribute this data to BIPM, there has to be some uncertainty between your fountain and the BIPM because of the satellite link. through GPS or two-way time transfer. So again, the random uncertainty is this big equation and comprises the quantum projection noise, which, as was said yesterday, is inversely proportional to the number of atoms, and it comprises the photon shot noise in the detection, comprises the electronics, and the local oscillator noise. So these are some of the components that affect your random uncertainty of the clock. And the systematic uncertainty, again, comprises, I'm not going to be able to go into the details of them, primarily the second order Zeeman effect, the collisional shift, the black body radiation shift, the gravitational shift. In our fountain, these were the four major effects which we had estimated. Again, I'll skip all these details and just show you, because Eckhart had described some of this in his talk, but some of the systematic uncertainties that we evaluated for our fountain was second order Zeeman was 50, and with an uncertainty of 0.06, 10 to minus 15, black body radiation so much, and finally we get a total systematic uncertainty, systematic shift of 39.8 with a net uncertainty of 2 in 10 to minus 15, and the random uncertainty was this. So with that, we did an international intercomparison sometime in 2015 or so, and the results are shown. This was done by two techniques: two-way time transfer using fixed communication satellites or global positioning satellites in common view. And the agreement between the fountain at NPL and PTB is within, I think the result is here, it agrees to pretty well within plus or minus 2, 10 minus 15. Subsequently, we have made a number of PIPM evaluations, and these are the results that are shown. And these results are usually published in the so-called PIPM circular T. And finally, worldwide cesium fountains results calibrating TAI, the International Atomic Time. There are over a dozen fountains worldwide, including ours, that contribute to calibrating the International Atomic Time. And this is a diagram taken from Stefan Weyer's recent publication, and there's fairly good agreement. I think it is a few parts in 10 to the 16 with respect to the International Atomic Time. So that's typically how accurate our cesium fountains are worldwide. Thank you very much for your attention.
Sen Gupta for his talk. And we have time for only 2 questions.
Yeah, well, I have a question. Do you have one fountain clock or 2?
I skipped that because there was no time. We are actually developing a second fountain. It's close to being completed. So why the second fountain? Because the first time you build something, you make some stupid mistakes. Right. So that's why, given an opportunity, you'd always want to build a second one, a better one. So there are some nice features in this. We use, instead of 001 geometry, we use a 111 geometry. We use the method of, another method of optical pumping to improve the signal to noise ratio, and a new microwave cavity design to reduce the cavity phase shift and so on. So there are some neat features in this second fountain. Okay, so it's not yet complete. Right.
We have time for one question. Well, I have to. I'm going to choose him because he's a student. So sorry. Yes, we choose you because you're a student, and students almost haven't asked questions.
Thanks. So I have a I don't know what kind of question, but I would like to know how much time it takes you to construct such a device, and how much resources you have to ask for, because, well, to do
how much time it took to construct the fountain and make it operational?
Yeah.
Well, I'd say close to about 8 or 9 years, or maybe 10 years. So it takes a long time. I mean, from absolute beginning, when you just started putting together things. So these are not quick and, quick experiments that you decide today and start making the fountain and build it complete within a year or 2 years, unless you have experience before in making and operating fountains. I mean, it's this. The second one will probably happen in 2 or 3 years. Yeah. So the second one happens much quicker.
During my PhD, I can do one of it, right?
Yeah, well, if you are planning to spend 7 or 8 years, sure. But then, no matter how long it takes, it's great fun. And another big advantage is, and basically it's a similar situation anywhere in the world. I mean, at PTB, Eckhart showed you wonderful results and so on and so forth, but what he did not tell you was they have been at it for the last more than 30 or 40 years. So it takes really long time before you become such experts. And your organization has to support this continuously in terms of funding, in terms of manpower, and so on.
And do you have any idea of more or less how much money it takes to do it?
Well, it takes a lot of money. All these, I can't remember exactly how much, but it takes a lot of money. Sustained funding. But the real good thing in this is, because this is a very small community worldwide, you get a lot of help from your friends all over the world. I mean, I must admit that in our effort to build the fountain at NPL, we've been helped considerably by our friends and colleagues in PTP, in NIST, and in Japan, and so on. Because there are only few players all around the globe. I mean, there are only eight countries in the world that are making the fountains, right? So, I mean, the same thing is going to happen to Mauricio. So I think you're going to get a lot of help from experienced friends all over the world, right?
We thank again Professor Sen Gupta for his